Welcome to the deep dive. Think about the last time you opened up the hood of a modern car.
Oh, good luck with that. It's basically just a giant piece of plastic now.
Right. I mean, if you go back a few decades, you could pop a hood and intuitively see how things worked. You'd say, okay, there's the engine, there's the belt, there's the
It
battery.
was mechanical. It made sense.
Exactly. But today,
Yeah.
it is a solid, impenetrable block of sensors and wires. You are staring at a highly complex system, and, unless you have the manufacturer's manual, it was completely unreadable.
Yeah, totally opaque.
And reading raw software code, especially a language like Haskell, can trigger that exact same feeling. You open a file hoping for a clean narrative, and instead you are hit with this wall of arrows, brackets, and like cryptic symbols.
It forces a realization that you are looking at an alien artifact. I mean,
Yeah.
without the decoder ring, those symbols just look like arbitrary punctuation.
Yeah.
And it is incredibly intimidating to try and parse what the machine is actually demanding of you.
Well, that intimidation factor is exactly what we're going to dismantle today. Our mission for this deep dive is to take a highly specific, very technical document and pull out a universally relatable aha moment about learning complex systems.
Which is such a satisfying journey.
It really is. So we're looking at a set of notes from a developer named Ang. Specifically, we're diving into part 115 of their notes on Haskell programming, dated April 25, 2026.
Part 115. They've been at this a while.
Oh, absolutely.
Right.
And we're going to decode the cryptic symbols of Haskell-type signatures, specifically the double arrow and the single arrow. And we're going to understand how data flows and how rules are enforced completely without needing a computer science degree.
It's totally doable.
Okay, let's unpack this, because looking at this raw code can absolutely feel overwhelming. But the true value in Ang's notes isn't actually the syntax itself.
Right.
The value here is the human element. We are looking at the very real, very frustrating story of a developer wrestling with an impenetrable system until the rules finally, wonderfully click into place.
Yeah, what's fascinating here is that complex programming breakthroughs, they rarely start from a desire to sit down and be clever.
Right, they're not trying to write a textbook.
Exactly. This entire journey starts from the most mundane, everyday place imaginable. It's just a developer simply needing to clean up a mess. Aang writes that their argument parser was getting incredibly complex. It was, getting messy, and that messiness was directly destroying the code's readability.
Let me push back on the phrasing there, though, because we hear this a lot in tech, this idea that code just gets messy.
Like it's rusting in the rain.
Yes, like it's a car rusting out just from the passage of time. But code doesn't get messy on its own. It degrades because we keep asking it to do more things.
That's a very fair point.
Think about a junk drawer in your kitchen.
Oh, no. I'm guilty of this.
Everyone is. You start off with a perfectly clean drawer, right? Maybe just a notepad and a pen. Then you buy a new type of batteries, so you toss it in there. Then you get some spare keys, a handful of rubber bands.
A random screwdriver.
Exactly. And throwing things into the drawer works for a while. It's fast.
Yeah, it's convenient.
But eventually, you want to actually find a single AA battery, and you realize you have to take the whole drawer out and organize it if you ever want to be productive again.
That is a brilliant way to visualize technical debt. Every new item you toss in makes the whole drawer harder to navigate.
Yeah.
And in Aang's case, the specific item they tossed in was a newly introduced feature. It was the format option, which could also be triggered by a shortcut, F.
Okay, so just a new way to format the output.
Right. But whenever you add a new flag or option to a command line program, you aren't just adding one thing. You're adding a whole web of logic.
Because it has to know how to handle it.
Exactly. You have to teach the program how to read the long name, how to identify the short name, what to use if the user doesn't provide anything at all.
Right, the fallback.
Yeah, and how to display the help text. So when all of that logic is just piled up in the main argument parser, your junk drawer, you lose the ability to see the structure of your program. You are blinded by the sheer volume of spare keys and rubber bands.
So Ang does what anyone with a chaotic junk drawer has to do eventually. They pull the drawer out and start sorting.
Is the refactor.
Right. To fix this unreadable mess, Ang extracts the specific format logic into a brand new, highly organized tool. They create a separate, reusable function called enum option. And this is a crucial transition for anyone listening who manages systems because it shows how developers actually solve chaos. They isolate the problem.
They isolate it and they build a dedicated container for it. So Ang builds the enum option function to handle all the heavy lifting for any option that behave like a list of choices.
Okay.
And the function is built to require 3 specific inputs to do its job. It needs the long name, which is a string like our format. It needs the short name, which is the character F, and a default value to fall back on.
But when you actually look at the mechanics inside this new enum option tool, Ang isn't just shuffling code around. They are actively building an organizer tray with very specific compartments.
It's very deliberate.
Let's look at what they're actually doing rather than just listing functions. They use something called an option as the base, but then they layer in a maybe reader. How does a maybe reader actually help clean up the drawer?
So a maybe reader acts sort of like a bouncer at the door of this specific function.
A bouncer.
Yeah. If a user types the command format, but then types potato instead of JSON or text.
Which users will absolutely do.
Oh, 100%. The program shouldn't just crash, right? The maybe reader intercepts that input. It looks at it and says, maybe this is a valid option, let me check. It attempts to read it, realizes potato is invalid, and safely handles the error rather than letting the entire system burn down.
That makes total sense. It's a safety net. And to figure out if potato is valid, Ang pairs that maybe reader with a lookup table. It acts as a translation dictionary. The user types a lowercase string, and the lookup table maps that string to the actual internal value the program understands.
Yeah, exactly.
They also hook up automated help text, and they use a function called showDefaultWith, so the user always knows what the fallback is. They even configure CompleteWith to enable auto-completion when the user hits the tab key.
Which is such a nice quality of life feature, and the way they generate that lookup table is a masterclass in efficiency.
How so?
Well, instead of manually typing out a giant dictionary of every single valid format option, Ang uses a sequence generator. It's written as minbound maxbound.
Wait, break that down, because minbound maxbound sounds like a math equation, but it's actually an incredibly elegant shortcut, isn't it?
It really is. Imagine you have a set of options, say red, green, and blue. Instead of writing code that explicitly says red is valid, green is valid, blue is valid, minbound maxbound simply tells the program, find the absolute lowest defined value in this category, find the highest defined value, and dynamically generate a list of everything in between.
Meaning, if someone comes along 6 months later and adds yellow to the category, they don't have to rewrite this in-option function at all. The boundaries simply expand automatically.
Precisely. The system adapts itself. And Ang even takes it a step further while drafting the notes. They realize they can extract the string generation out of that table.
Oh, interesting.
Yeah, they use a piece of logic written as options treeness table.
Map first.
Yeah, the FIST stands for first. It simply means the program grabs only the first element, so the string name, from every entry in that dictionary, creating a clean list of valid strings to show the user in the help menu. It's a continuous process of refining the logic so it takes up less and less mental space.
Here's where it gets really interesting, because Ang isn't just fixing the format option anymore. By extracting all of this into enum option, they're generalizing the solution.
Yeah, they made a universal tool.
They're building a tool that can handle any list of options, as long as it fits a pattern. But wait, if this in-option tool can now accept anything, isn't that incredibly dangerous?
How do you mean?
Well, if I build a generic slot and machine, couldn't a user just crash the system by shoving a totally incompatible piece of data into it?
Yes. That is the exact vulnerability you open up when you build generic tools. If it accepts anything, it can break on anything. And that problem brings us right to the first cryptic symbol in Ang's post, the double arrow.
Ah, okay.
The equal sign followed by the greater than sign.
Let's look at the actual code Ang wrote for this, because this is where the alien symbols really start. The new type signature for this function begins with this phrase, show A, enum A, bounded A. Let's ignore the arrow for a second. What is actually happening inside those parentheses?
We are encountering a concept called type class constraints, which is deeply tied to something known as ad hoc polymorphism.
And there's the terrifying computer science jargon.
I know.
Ad hoc polymorphism. Let's demystify that for the listener, because it sounds like a disease.
Fair enough. Let's start with polymorphism. Poly means many, morph means forms. In programming, it just means our function can work with many different types of data. It's flexible. Okay. In Ang's code, that flexibility is represented by the lowercase letter a. The letter A just means any type.
Got it. So A is a placeholder for whatever random data we decide to throw at our generic tool. But what about the ad hoc part?
This is the crucial distinction. Ad hoc means the function behaves differently depending on the specific type of data it receives.
Hmm.
It doesn't treat everything identically. It needs to know how to interact with the specific data you give it.
So it adapts.
Exactly. And if we connect this to the bigger picture, building a flexible system is great, but building a flexible system with no rules is a recipe for complete structural collapse.
Right.
The program absolutely must demand proof of capability before it allows the code to run. Ang defines the double arrow, the MyMel arrow, as a strict contract that the type must fulfill.
I love the contract analogy. It's universally applicable. Think about renting a car. The rental agency, which represents our enum option function, says, look, we practice ad hoc polymorphism. We rent cars to anyone. I don't care if you are a baker, an accountant, or a professional athlete. That is type A. You can be anyone.
The agency offers total flexibility on who you are.
But the agency says, to actually drive this specific car off our lot, we have a contract. That is the double arrow. The terms of this contract state that you must show me a valid driver's license and you must show me a valid credit card. You can be anyone, but you must possess those specific required capabilities.
That is a perfect mapping of the concept. In Ang's code, the driver's license and the credit card are the behaviors labeled show, enum, and bounded.
How do those behaviors actually act as a license and a credit card?
Well, the contract, show A, enum A, bounded A, literally tells the compiler, I will accept any type of data, but only if it can prove three things.
Okay, what are they?
First, it must know how to convert itself into a string of text. That's show. Second, it must be able to be sequenced in an order, like counting 1, 2, 3. That's enum.
Right.
And third, it must have a defined minimum and maximum limit. That's bounded.
Oh, which perfectly explains how they were able to use min-bound, max-bound earlier.
Yes.
The compiler knows it's 100% safe to ask for a minimum and maximum boundary because the contract guarantees that whatever data passes through will have those limits built in.
Exactly.
If you try to pass in a type of data that goes on infinitely, the compiler acts like the rental agent seeing a fake ID. It stops you right there and says, contract violated. I am not letting you drive this function.
It is a brilliant, uncompromising mechanism for safety. The double arrow is the gatekeeper. It establishes the rules of engagement before a single line of actual work is executed.
Okay, so we showed our ID, the contract is signed, the rental car is ours. Now we transition from the strict rules of the code to the actual physical movement of the data. And this brings us to the second half of Ang's complex type signature. The single arrow, a hyphen followed by a greater than sign.
Once the constraints of the double arrow are satisfied, the rest of the signature describes the transformation of the data. The single arrow denotes mapping an input value to an output value. So after the contract, Ang's signature reads, string char a parser A.
This represents a sequence of inputs leading to a final output. And Ang provides a fantastic analogy here to visualize this flow. They say to think of the single arrow as a literal conveyor belt in a factory.
Let's follow the data down that belt.
Yeah.
We are standing at the start of the line, placing our inputs onto it one by one. First, we put down a string. In the case of our format option, that string is the long name, the word format.
Okay.
The conveyor belt moves forward. That's for sports. And then we place down a char, a single character.
Yep.
This is our short name, the letter F.
Right.
The belt moves forward again at E. Then we place down A, which we established earlier is our flexible but contract-abiding data type. Here, A serves as the default value for the option.
So at this point, you have officially loaded all your raw materials onto the line.
Exactly. The belt moves one last time, A, and it deposits everything into the final output, the end of the line. Ang's signature says the output is parser A. Ang says if A is the product being shaped on the conveyor belt, then parser A is a boxed product. But Ang also calls parser A monadic context. I'll be completely honest, that phrase sounds like academic nonsense to me. What on earth is a monadic context, and what does it mean for our conveyor belt?
A monadic context is one of those phrases that terrifies people learning Haskell.
It's terrifying me right now.
Right. But Ang's box analogy is actually the perfect way to understand it. The conveyor belt takes all these raw materials, the string, the character, the default value, and it shapes them into a final product, A. But the factory doesn't just toss that raw, loose product out the door to the rest of the program. It places it inside a highly specialized box, which is the parser context.
But why does it need a box? I mean, if the product is finished, why not just hand it over to the rest of the code?
Because the real world outside that function is messy and unpredictable. Think about shipping a fragile item. You don't just hand a delivery driver a loose glass vase, right?
No, of course not. You pack it in a box with bubble wrap.
Exactly, so it survives the journey.
Mhm.
In software, what if the user types the command line argument wrong? What if the data doesn't parse correctly? By putting the product A into the parser box, you are wrapping it in protective capabilities. The box itself knows how to handle a failure.
Oh, I see.
The box knows how to trigger those error messages and help menus we talked about earlier.
Hmm.
So when the rest of the program receives this boxed product, it doesn't have to worry about the item being broken. The box manages all the complex states and potential side effects safely.
Wow.
So the single arrow moved our data from raw inputs down the assembly line and safely into its required packaging.
It's beautiful when you step back and see the machinery working. What started as a chaotic junk drawer has been completely transformed into a highly efficient, heavily regulated factory line. And this brings us out of the microscopic view of the syntax, back to the deeply human feeling of learning.
Yeah, Aang writes a final reflection while drafting this post. After wrestling with the messy parser, extracting the reusable tool, writing the strict contract with the double arrow, and building the conveyor belt with the single arrow, they write, I think I finally started to grok Haskell-type signatures. It's a satisfying feeling when the syntax starts to click.
Grok. It's such a great word.
It really is.
To understand something intuitively or by empathy, to not just read it, but to truly get it in your bones. We've all experienced that sensation, whether you are learning a new programming language, trying to read sheet music, or figuring out how to navigate a massive corporate bureaucracy.
Definitely.
For the longest time, you were just staring at the alien artifact. The symbols make no sense. You are rigidly following rules you don't understand, just hoping the system doesn't crash.
But then you hit that critical threshold, the friction disappears. The language stops being a barrier to your thoughts and actually becomes a tool to express them. You stop seeing a double arrow as a confusing piece of punctuation, and you instantly see the bouncer checking IDs. You stop seeing a single arrow as just a hyphen in a bracket, and you see the conveyor belt moving your data into its protective box. It is an incredibly profound, satisfying feeling.
It is the ultimate reward for the struggle. Let's recap what we've actually uncovered here, because we've traveled from chaos to clarity. We started with a messy, unreadable junk drawer of an argument parser. The code was doing far too much, blinding the developer. So Aang isolated the problem and built a reusable tool called a NumOption.
Right.
But to make that generic tool safe, they had to sign a strict contract using the double arrow. That type class constraint proved the data had the right license and credit card to drive the function.
And once that contract was signed, they sent the data down the single arrow conveyor belt, transforming raw strings and characters into a safely packaged monadic product, perfectly ready for the rest of the program to use without fear of breaking.
And the result of all that technical heavy lifting was a moment of pure clarity for the developer. A genuine aha moment, where the impenetrable alien artifact finally became a readable manual.
This raises an important question, though, and I think it's the perfect takeaway for anyone listening, regardless of whether you ever write a single line of code. Aang achieved this incredibly satisfying click of understanding, this moment of finally grokking the system in part 115 of their notes.
Wow. Part 115.
Part 115. It took persistent, continuous effort and repeated failure to reach that moment of clarity. So what complex, seemingly impenetrable system or foreign language in your own life or work might suddenly make perfect sense if you just gave yourself the grace to break it down piece by piece?
It's a great thought.
What wall of cryptic symbols might melt away into a beautiful, functional conveyor belt if you just keep showing up, even if it takes you 115 tries to finally grok it?